and Physics 100 students and random YouTubers who are looking for interesting physics stuff. Today's lecture is, I think, a fairly interesting one, at least to me, because I'm an astronomer. And gravity, of course, always fascinates me. This week we'll actually have two chapters that we'll cover, both kind of shorter lectures, so a couple 30-minute lectures with a few equations and a few sample problems. Our goal for this first lecture this week is to understand gravity. Our objectives, we're going to learn about who actually discovered what about gravity. It's not going to be quite what we expect. We're going to learn about the universal nature of gravity and how that affects our universe. We're going to explore the gravitational constant, which is just a value. We'll learn about how gravity is responsible for tides. We'll see how gravity changes when you're on the inside of a planet, and how gravity can lead to black holes. So we get to learn about black holes a little bit, even though we won't really do any homework or test questions about black holes, so at that point we'll be able to skip over it. Unless you really want to learn about black holes, which I think a lot of you probably will. So let's get started. So, who discovered gravity? Discuss this with a neighbor, a roommate, your pet, maybe your goldfish knows. And I bet in the name that you're learning out towards the computer, as I've encouraged you to do, is probably Newton, because Newton gets a lot of credit for discovering gravity, doesn't he? But you should think about it. When Newton discovered gravity. Gravity. Pretty sure people knew about that before Newton. That things tended to fall when you dropped them. So, Newton actually did not discover gravity itself. Gravity was known about a long time ago, thousands of years ago, even by the ancient and classical Greeks. They knew that gravity existed. In fact, Aristotle made an argument, a scientific-ish argument, that the Earth was the center of the universe based on gravity. That he noticed that the densest objects tended to congregate to the center. So if you take a cup full of pond water and some pond mud and shake it up, the densest particles will settle out first, and then the lighter ones will be on top of it. And since the Earth was clearly to him more dense than anything he could see in the cosmos, therefore the Earth had to be the center, in his argument. Of course, his argument was not correct, but he actually made an argument based on gravity, and this was over 2,000 years ago. But what was not known at the time is how far gravity went, or what kept planets into orbits around whatever object you thought they orbited around at the time. In fact, when Kepler discovered that the sun did, in fact, not orbit the Earth, in fact, the Earth orbited the sun, the planets all orbited the sun, he had no idea why they orbited the sun. No idea at all. Just that's what happened. And it wasn't until Newton came around that it was figured out that gravity was the culprit for orbits. What Newton realized that no one else had before was that gravity extended far beyond the surface of the Earth. Now, the apple metaphor is completely empty. He didn't get hit on the head and realize that. He figured out how gravity affected the orbits and how that played with Kepler's laws. That gravity was truly universal. Before this time frame, it was thought that the Earth had one set of laws and the universe had another set. And what Newton discovered the first time is that those laws were in fact the same. The same laws that govern us here on planet Earth are the same laws that govern our galaxy, our solar system, our universe. But it does fall off with distance. It does weaken with distance. That's called the inverse square law, and it's exactly as it sounds. As you get further away from the center of an object, the center is always the important part. The force of gravity falls off as the distance squared. So if I go above the Earth and get away from the Earth, here's the Earth and here's me. If I go away from the Earth, the force of gravity falls as the distance squared. So if I go to one extra Earth radii, instead of my weight being 1,000 newtons, my weight is now 250 newtons because I have to square the 2. The moon is 60 times further from the center of the Earth than we are. So if I'm on the moon and I ask how much is my gravitational force on me from the Earth, I take 60 squared, which is 3,600, and I take my current weight of 1,000 newtons and divide by 3,600, and the answer is 0.3 newtons. So that would be the force, the gravitational force the Earth exerts on me from the moon, 0.3 newtons. Now, the moon exerts 160 newtons of force on me, so I would pretty much stick with the moon at that point. And I think I just kind of answered that question. So, what does it look like? So the more mass I have, or the more mass the Earth has, the more the gravitational force on it. So it's proportional to mass 1 times mass 2. This is very quickly turning into a Dr. Seuss book. And it's proportional to the inverse of the distance squared. So it's mass 1 times mass 2 divided by the distance squared. But that's not the complete equation, because I now need to calibrate it. So how do I calibrate it? I calibrate it by putting a constant in front. This constant is big G, not to be confused with little g. Big G is not 10 or 9.8. Big G times mass 1 times mass 2 divided by radius times radius. Now, quick note, the radius. How do you calculate the radius? Always confusion on this. You take the centers of the two objects and take the distance between those centers, and that is what you use for radius. So, again, I will sometimes throw distractors at you to see if you understand the concept. So let's do a quick sample. By the way, the big value for big G is 6.67 times 10 to the minus 11th in physics units. I know this is the physics units. Don't worry about that. It's a lot of stuff, but as long as you're using physics units, you'll be okay. And radius is the distance between the two objects. So let's have a 3 kilogram and a 4 kilogram object separated. Let's do this. Let's make the radius of, this is what I did for trying to create things off the top of my head. Here's my center, this distance. So the radius of, this is A, which has a radius of 0.02 meters. And has a mass of 3 kilograms. This one has a radius of 0.03 meters and a mass of 4 kilograms. This is not drawn to scale, obviously. And the distance between here and here is, let's call it 0.15 meters. Okay. Now, let's calculate the gravitational force between these two objects. In order to do this, you're going to have to figure out what that radius is. And notice it's radius times radius. It's the same value twice. So don't use 0.02 and 0.03. Multiply those two together because that won't work. So go ahead and try to calculate the radius. Go. All right, if you need a hint, how far is the center of this from the center of that? Go. I need this distance. All right. Now, in this case, and each time the case will be different depending upon how the values of the things given to you. I have to have this distance to this distance to this distance. My radius is going to be 0.02 plus 0.15 plus 0.03, which is 0.2 meters. Because I didn't give you this distance. Now, if I gave you this distance, you wouldn't need to know any of that. None of this would matter if I gave you that value. So that's my radius. So let's now calculate it. Force equals big G times 3 kilograms times 4 kilograms divided by 0.2 squared. All right, so G is 6.67. I like to use 20 over 3, just because. So I have 20 over 3 times 3 times 4 divided by 0.2 squared times 10 to the minus 11th. I have to keep 10 minus 11th. So I've got 80 divided by, this is a fifth, so 1 over 25. So this is going to be 2,000 times 10 to the minus 11 times 10 to the minus 11. So this is 2 times 10 to the minus 8 newtons. A very, very small force because they're a fairly decent distance and they're fairly small mass. All right. Now, so let's do another quick one. Actually, let's see if I have one here. I don't. Okay, let's try another one. Because, well, let's face it, this is the only equation we have today. Or, sorry, for this lecture. All right. Let's take an object. Let's take 2 asteroids. Asteroid 1 and asteroid 2 has a mass of, let's see here, let's give it a radius of 100 meters. I'm trying to calculate masses. Let's see here, we got a volume of 4/3. Radius squared, that's 10 to the 6. That's 4/3 pi. It's 4 times 10 to the 6. Let's say 1.0 times 10 to the 6 kilograms. And asteroid 2 will have a radius of 2 meters. So it's going to be 8 times 4. So let's say it has a mass of, I forgot. Water's 10 to the 3rd, not 1. I'm an astronomer, so the density of water is 1 gram per cubic centimeter. So this is going to be 8,000 kilograms for the mass. And these two objects are separated by a distance of 2 times 10 to the 5th meters, so 200 kilometers. All right, now calculate the force. Now, in this case, 102 or so is much smaller than 200,000, that we can ignore the fact of whether we're actually, I gave the distances between the centers or not, unless we want to do things uber accurate, which what the numbers I've given you is not really the case. So, the radiuses of these two objects don't matter. What matters is the distance between the centers, which in this case is 2 times 10 to the 5th. So we have G, which is, I like to put 20 over 3 times 10 to the minus 11th. And the amount of sig figs we're using, this is a good approximation, times mass 1 times mass 2. And I just turn this to 8 times 10 to the 3rd. And as long as we're doing everything in physics units, it'll work out to newtons at the end, divided by this square, which is going to be 4 times 10 to the 10th. When you square a number like this, you have to square both the number in front and the exponent. All right, so now we do the math. And we have, let's see here, we have 20 times 8, which is 160, divided by 12, which is 3 times 4. By the way, when you have a fraction within a fraction, this number goes to the other side. If I had a fraction here, that would go to the top, but we don't spend this. All right. We have times 10 to the minus 11, plus 9, plus 3, minus 10, which is 12 minus 21, which is minus 9. So the force is, let's see here, this is going to be, let's change this to 16, and that's minus 8. I'm just doing math without a calculator here. So we have let's call it 1.3 times 10 to the minus 8 newtons. All right, so not a whole lot of gravitational force between those two objects. All right, hopefully that clarifies that, and that's basically the only equation we have for this lecture. So everything else is going to be concepts. All right, tides. What causes the tides? And if you answered the moon, you're 90% correct. If you answered the sun, you're 10% correct. Sort of. At least for the object that's the culprit. Now, what is the physics behind it? Well, if we look at the Earth and the moon, so let's do that here. Let's say this is the moon and this is the Earth. Well, this part of the Earth is closer to the moon than this part. And since the force of gravity drops with the radius squared, that means that this part of the Earth is going to experience more tug from the moon than this part. And as a result, the Earth is going to get stretched. And that stretching is called the tides. The tides are hugely a function of proximity. It actually becomes radius to the fourth, and of course mass. And so the Earth gets stretched, the water gets stretched by about 1 meter, the ground gets stretched by about 6 inches, and the air gets stretched as well. Since the Earth rotates, the position of the stretching actually points about 10 to 15 degrees away from the moon. So if you see the moon directly to the south, the high tide is already past you by about 1 hour. And then, of course, 12 hours later, actually 12 hours and 50 minutes later, you get the next high tide. Well, after the last high tide. So the highest high tides occur when the moon is closest to the Earth. Also, since the moon and sun are both tugging, you have to worry about the relationship between those tugs. So on Earth, every 24 hours and 50 minutes, did I say 12 hours and 50 minutes? That was 12 hours and 25 minutes, sorry. Every 24 hours and 50 minutes, because the moon rotates and orbits around the Earth, you get 2 tides, 2 high tides and 2 low tides per day. And it changes by 50 minutes because the moon rises 50 minutes later each day because it orbits around the Earth once every 29.5 days. Well, actually one every 27 days, but there's a couple of versions of the month. I won't get into that. So the sun also affects our tides. If the moon and the sun are in the same line, we have the biggest tides. And it doesn't matter which side of the Earth the moon is in, we get the biggest tides. When the moon is 90 degrees away, we get the smallest tides, meaning the lowest high tide and the highest low tide. We call, when it's halfway around, we call those the quarter phases. So first quarter and third quarter, the moon would be half lit and half not lit. When the moon is a new moon or full moon, we get the biggest tides. So the highest high tide and the lowest low tide. Also, the moon has a elliptical orbit, and so sometimes it's close to the Earth, sometimes it's further away. So if the moon is the closest point to the Earth in its orbit, called perihelion, or sorry, perigee, helions around the sun, you get the biggest tides. And if it's at the furthest point, apogee, then you get the smallest tide. So if you combine those together, and the perigee is at the full moon or new moon, then you get the biggest tides of the year. And if it's at apogee at the quarter phase, either first or third, then you get the smallest tides of the year. In addition to that, of course, the Earth exerts tides on the moon. So imagine this is the moon and I'm the Earth. The Earth exerts tides on the moon, so it stretches the moon a little bit. However, those tides are locked into place because the time it takes the moon to go around the Earth is the exact same as the time it takes the moon to rotate. And so that means that the same part of the moon is always approximately in the same position as viewed from the Earth, same view from the Earth. So our view of the moon doesn't change much. We don't get to see the backside of the moon other than through photographs taken by NASA or other space agencies. And so that means that the high tide of the moon is locked into place. On the Earth rotates. And since the Earth rotates and the moon's sitting here, the location of the high tide is like this. And so the Earth rotates past the position of the high tide. And so that's why the tides go up and down, is because we rotate from high tide to low tide to high tide to low tide again as we rotate around every 24 hours. And so for the Earth, they're not locked in place, but for the moon, they are. In fact, almost all of the moons in the solar system have their tides locked into place, or approximately locked into place. We call this tidally locked. In fact, Pluto is tidally locked to its largest moon, Charon. So if you're standing on one side of Pluto, you would see Charon in the same part of the sky all the time. And if you're on the other side of Pluto, you wouldn't even know Charon existed. If you're on the moon, on the near side of the moon, you would see the Earth in the same part of the sky, approximately would wobble back and forth slightly over the course of the month, but just very slightly. In the same part of the sky, even though the sun rises and sets and all the stars move around once per month. And if you're on the other side of the moon, the far side, you wouldn't even know the Earth existed. But there's more. So, interesting fact, fun fact, as I become shoulder deeper for the next couple of minutes. The Earth's bulge points away from the moon slightly, so that means the moon gets to tug on the bulge and pull it back. The Earth rotates this way, and so it actually pulls backwards and slows down the rotation of the Earth by about 2 milliseconds per day per century. Meaning 100 years from now, the length of our day will be 2/1000ths of a second longer than it is today. Now, energy has to be conserved, including angular energy, and momentum has to be conserved, including angular momentum. And so as the Earth slows down, the moon has to speed up in its orbit. As it speeds up in its orbit, it gets further from the Earth. And so it's actually moving away from us by 4 centimeters per year each and every year. So about 1.5 inches. How do we know this? Because, and I'm sorry any of you out in TV land, or computer land, I guess, internet land, that believe that the moon landings were a hoax. I'm going to have to step on your toes right now. The moon landings did in fact occur. And we know this because there are very specialized mirrors on the moon that had to be set up by astronauts that reflect light directly back to the Earth. Usually if light bounces off of a mirror, it comes off at the angle it hit. And so if you're standing here and you send the light wave this way, it doesn't come back to you. Unless you build the mirror specifically to have a shape so that no matter what angle you send the light at, some amount of it, about 7% usually, comes back to you. And that's the kind of mirrors we have on the moon, but they have to be very specifically set up to do that. And so we can bounce light beams off of the moon, measure how long it takes to get back, and use that time with this knowing the speed of light to calculate the distance to the moon. And that distance has been increasing each and every year. Yes, this means that the moon was once much closer to us. If you rewind the tape about 4 billion years, it means the moon was about 10,000 miles from the Earth when it was formed and then moved outwards. And the length of our day was closer to 20 hours 4 billion years ago. All right, what about gravity inside of an object? Suppose I dig a giant hole in the Earth. And I go down, climb down into the hole. So I have a little ladder here. Pretend that's a ladder. My drawing skill would do. All right, as I go down to the Earth, will the gravitational force increase, decrease, or stay the same? Think about that. This is a tricky question. And one that, if you just look at this equation here, is going to lead you astray. Because there's something going on here. If we look at the big picture, draw a line all the way to the center of the Earth. And let's say I'm here. Let's look at the gravitational forces on me. Everything below this line will pull me this way. Everything above this line will actually pull me the other way. Now, there's a lot more mass here, but this mass is much closer to me. And so when you do the math, it turns out that everything cancels out except this little circle here. So it turns out when you dig down into a planet, the only mass that counts is the mass that's at a smaller radius than you. So everything outside of you cancels out, and only the mass inside of you counts. And since that mass is much smaller, it turns out as you drill into the Earth, your weight, your gravitational force on you would actually decrease. In fact, if you're at the exact center of the Earth, every piece of mass would pull you in the opposite direction, and your weight gravitational force on you would be zero. All right. Black holes. The following is not part of our course, so if you want to skip over to the end or just go to the next lecture, feel free to do so. If black holes seems like a really interesting topic, then go ahead and stick around for the next couple minutes as I talk about how gravity creates black holes. Because it's just really cool, and why have a physics class and not learn about black holes? They're just so cool. Well, figuratively and literally. So, the first thing I have to talk about is escape velocity. If I throw a pin up in the air, it comes back down. If I throw it a little bit harder, it goes a little bit higher. And if I throw it really hard, you're not going to be able to see this, but it's going to hit the ceiling. Okay. Only one pin was harmed in the making of this film. If I went outside where there's no ceiling, and I throw it harder and harder, it's going to go higher and higher. At some point, if I throw it hard enough, it will not come back to the Earth. It will escape the gravity of the Earth and never come back. That velocity is called the escape velocity. Escape velocity depends on two things: the mass of the object and the radius of the object. The bigger the mass, the bigger the escape velocity. The bigger the radius, the smaller the escape velocity, because gravity drops off as the radius squared. So if I took the Earth and added more mass to it, the escape velocity would go up. If I kept the Earth the same mass and shrunk it down, the escape velocity would go up on the surface of the Earth. Now, at some point, the escape velocity of an object would get so large that it would become the speed of light. And Einstein discovered that nothing could travel through space faster than the speed of light. There's a loophole, but nothing can travel through space faster than the speed of light. So therefore, nothing, not even light, could escape from the black hole. Now, how big would the Earth need to become in order to turn the Earth into a black hole? And I cover this in case any of you out there are science fiction writers, so that you don't make this horrible, horrible, hideous mistake with black holes. There's a movie out there that had a black hole like this, floating above the surface of the ground, and it was about that big in size. And unfortunately, what the writers of the movie did not realize is that the mass of that black hole would be the mass of Jupiter, in that it would not just stay there, it would pull the Earth towards it, and actually would break the Earth apart tidally. The Earth would be destroyed instantly. Oops. So please don't make that mistake. I turn off movies at that point when they make those kind of mistakes, especially if it's part of their plot. And this it just got worse from there. So how big would the Earth be? Well, the Sun, which is about 250,000 times the mass of the Earth, would have to be shrunk down to the size of downtown Indianapolis to become a black hole. It would have to be 3 kilometers in diameter. And it turns out black holes are linearly proportional to their mass in terms of size. So that means it would have to be 250,000 times smaller than downtown Indianapolis. Which means that it would have to be shrunk down to about the size of my pinky, the end of my pinky. 12 millimeters. It'd have to be 12 millimeters in size, half an inch in diameter. Half an inch in diameter. You'd have to shrink the Earth down and turn it into a black hole. Okay, so instead of shrinking the Earth into a black hole, let's add more mass and turn the Earth into a black hole. How much mass would I have to add to the Earth to make the Earth a black hole? Now again, the Sun is 250,000 times the mass of the Earth. We call this one solar mass. The Earth, to be turned into a black hole, would have to be given approximately 4,000 times the mass of the Sun to be turned into a black hole. So you really have to It's really hard to make a black hole. Really hard. Now, there's no escaping from a black hole, and so we call the effective radius of the black hole, which is where the escape velocity would be the speed of light, not the actual physical radius of the black hole, because that goes to the center. It's called the Schwarzschild radius. The Schwarzschild radius is called an event horizon. Now, an event horizon is a fancy term in science that just basically means goodbye forever. So if you have a friend that at the end of the year is going to go off to some other college or to some job in some other state, and you're never going to see them again, and you're happy about that, when you last see them, you just wave and say, event horizon. Just hope that they haven't watched this video as well, because they'll turn and smile and go, well, event horizon to you then. You are welcome at the end of the semester to say event horizon to me, or post that in comments. I don't take too much offense at that, because I know at the end of the semester you don't want to see your teachers again. Just the way it goes. So event horizon means goodbye forever. When you pass through an event horizon, you're never coming back. And if you come back, you actually go to a different universe. A little bit of we're not quite sure what happens, but that's what we think. But there's more. It turns out there's a relationship between time and space. That's why we call it space-time, and why we call it relativity. And therefore, when you warp space, that's what gravity does. Gravity warps space. And when you warp space, you also warp time. Now, this equation we're not going to use in class, but it just did wrong. I never fixed it. Yeah, there we go. The time that passes by for an astronaut equals the time that passes by for the universe times the square root, that's what that funny 1/2 power means, but I don't have the square root symbol very well in PowerPoint, times 1 minus what's called the Schwarzschild radius divided by r, where the Schwarzschild radius is 1.5 kilometers times the mass of the object in solar masses, in other words, in terms of mass of the sun. And so as time slow down, and then when you hit the event horizon, which r should equal r, 1 minus 1 is 0, so time would stop. Your clock, as viewed from the universe, would stop. At least in real time. Once you go into the black hole, time would become imaginary. What does that mean? I have no idea. It just sounds really cool. All right, so I'm just going to answer this one for you since it's not part of our class. What happens if we were to take our sun and replace it with a black hole of the exact same mass and at the exact same distance? Well, it turns out not much would happen. The Earth would freeze, of course, because we no longer have the sun warming us up, but the time clocks of the Earth would remain the same because we're still the same distance from the object, and the Earth's orbit would stay the same because the mass hasn't changed, and the mass determines the orbit. So the only thing that would happen is we would freeze. The only time you really recognize a black hole and its effect on time is when you get really, really close to the black hole, meaning that you're much closer to the black hole than the physical radius of our sun. So once you get to, say, 100,000 miles, our sun has a radius of a diameter of 800,000, almost a million miles, 900,000 miles, then you would really start to notice the effects. But by the way, you can't get sucked up by a black hole. Black holes are really tiny, and you have to actually aim at the black hole, and trying to aim at a 3-kilometer object from 93 million miles away is really extremely difficult. And if you miss it just by 1 kilometer, you get slung shot around the black hole and out of the system. Now the question is, can we see black holes? The answer is no, not directly, because light can't escape. Well, not very easily. There's something called Hawking radiation, we're going to cover in just a moment. But we actually find black holes indirectly. We do know they exist. We actually have observations that tell us that there are black holes in our universe. So we'll see stars that we can see in orbit around these black holes, or vice versa, the black hole orbits the star. And from that we can determine the masses of the objects and how far apart they are. Well, when we look at the center of our galaxy, and actually I have to update this number because I wrote this lecture too long ago, we see stars orbiting around the very center of our galaxy in a very small orbit, where in the center of the galaxy they orbit within about less than a light year of the center of the galaxy, in such a way that we can tell that the very center of our galaxy, the very center light year of our galaxy, has about 4 million solar masses in it. And the only way you can get that much mass in that small of a location without being able to see it, because we can't see this mass at the orbit around, is to have a black hole. So we have a 4 million solar mass black hole in the center of our galaxy. And the Andromeda Galaxy, which is the closest spiral galaxy to us and is headed towards us, is going to collide with us in about 3 to 4 billion years, has about a 1 billion solar mass black hole in the center. And some of the most massive black holes we've spotted in the centers of very giant galaxies are about 80 billion times the mass of our sun. 80 billion times the mass of our sun. So there are very large black holes out there. There are also very small ones, ones that are a few times the mass of our sun. But they're very rare. There's only one every few thousand light years, so don't worry, you're not going to automatically be sucked up by them. Death of black holes. Turns out nothing lasts forever, not even black holes. And the thing I like about this is I get to use the word Google, not in reference to the company, but in reference to the number, Googal, which is 10 to the 100th power. That's 1 followed by 100 zeros. So why is that number important with black holes? Well, it turns out that energy can actually quantum tunnel through the event horizon of a black hole. Or, also, energy can be created and destroyed just outside the event horizon. Particles and particles with positive and negative energy are being created in our universe on a very, very small scale. We're talking like 10 to the minus 34th meter scale. We call this the quantum scale. All the time. If you're just outside the event horizon of a black hole, the negative energy particle will fall